Okay, so today we're going to go ahead and talk about kinetic energy, the work kinetic energy theorem, and solve a problem involving the work kinetic energy theorem. So let's think about what you know about kinetic energy. So kinetic energy is just the energy of motion. So anytime something is moving, this is just the energy something has. So it's the energy when something is moving. So I'm going to go ahead and write down our equation for kinetic energy. So our equation for kinetic energy is Ke equals 1/2 mass times velocity squared. Well, let me go ahead and write down my given. So we know m stands for mass. We will oftentimes want that in kilograms. And v stands for velocity. And we will oftentimes want that in meters per second. And Ke, that we know is kinetic energy. And energy we know will oftentimes be measured in joules. And you can definitely use other units as well, but these will be the SI units that we will consistently use when solving problems. Okay, so now let's go ahead and talk about another thing. Oftentimes we care about the quantity of something, but more importantly is the change of something. Like, how are we changing? How are we growing? How are we increasing, decreasing? Whatever it is, change is important. So let's go ahead and talk about change in kinetic energy. So we know to write change, we use the symbol delta. So delta K, it's Ke. So the change in kinetic energy, if we want to find the change in something, we are going to subtract our final value, whatever that is, and then take away our initial. So we're going to take away our initial kinetic energy from our final. So that'll be Ke final minus Ke initial. Cool. Let's go ahead and add a little more detail because that might be handy sometimes. We know that Ke is 1/2 mv squared, and Ke initial is 1/2 I squared, and this should be Vf squared. I put this there because mass oftentimes doesn't change. Mass will be usually pretty consistent when we solve problems. Oftentimes it'll be the velocity of something that will change. Cool. So this is going to be our equation for change in Ke. So if you do work on a system, you will either increase or decrease the energy, which oftentimes specifically the kinetic energy of the system. Okay, so if I'm going to write that down, sorry about that. Okay, so if you do work on a system, you will increase or decrease the energy of the system. And oftentimes we will deal with the kinetic energy increasing or decreasing. So we know that this is going to be the work total. Because of this is going to be equal to the change in energy. So this is 100% true right here. Work total will always equal the change of energy. So if work is positive, then the Ke will increase and get bigger. More kinetic energy. Things will be moving faster. There'll be more energy. If work equals negative, I should have said that, the energy will decrease. There'll be less energy overall. Oftentimes when we solve problems, as long as other types of energy aren't changing, we will oftentimes use the work total is going to be equal to the change of Ke. So this equation we'll be able to use 90% of the time. So again, if work is positive, then the energy or kinetic energy will increase. And if the work is negative, the energy or kinetic energy will decrease. And I want to think about what is something that will oftentimes do negative work on a system. A good example of that is like friction. Friction will always do negative work on a system. Do negative work on a system. So it will take away energy from a system. Okay, so we're now going to go ahead and solve a problem involving the work kinetic energy theorem. So let's go ahead and read the problem and draw some things out. Okay, so a box of mass 2 kilograms is sliding across a frictionless wood floor at a speed of 3 meters per second. Okay, the box suddenly enters a rough patch. Here's our rough patch, and slows down to a stop over a distance of 4 meters. Okay, Okay, so then here it is at the end. So we know if it slows down to stop, our final velocity is going to be 0. Okay, calculate the force of friction between the box and the rough patch. Since I know this is going to deal with forces, I am always going to draw a free body diagram for this. So here it is on the rough patch. We know we have the force of the surface pushing up on it. We have gravity pushing down. Force of gravity will be 20 newtons. Force normal will be what? It's not moving up and down in the y direction, so we know those two will have to balance out. Will be 20 newtons. There's nothing pushing it to the right. It's just moving that direction because of its own inertia. Friction is going to slow it down, so that is going to be pointing to the left. Cool. So work kinetic energy theorem is going to be useful whenever we have forces acting on an object and the velocity is changing. There's definitely other strategies we can use to solve this problem. We can use like F net equals ma and the constant acceleration equations, but let's go ahead and solve this using the work kinetic energy theorem. So our new equation is work is going to be equal to the change in kinetic energy. So change in kinetic energy we know is 1/2 mvf squared minus 1/2 mvi squared. Okay, work we know is our force times our displacement if we're dealing with constant forces, which we are in this case. The force of friction is not like a function that depends on, it's just going to be a constant number. So I'm going to call this the force of friction. So we know work is defined as negative if the force and displacement are in opposite directions. In this case, let's see, the force is pointing to the left and the displacement is to the right. So this is going to be negative work. Keep in mind, we can ignore the work done, or there is no work done by gravity and the normal force because there is no motion in that y direction. So we're only going to deal with the force in the x direction when we're calculating work. Okay, so we have all these things. Let's go ahead and plug things in. So we want to find force of friction. That's going to be my unknown. Displacement is 4 meters. So 1/2 mass is 2. Final velocity we know over here is just 0 squared. Take away what? 1/2 mass is 2 times 3 squared. Great. Oh, the first term cancels out. Love that. So now we just have negative FF times 4 equals, this will just be negative 9. So then when we go ahead and solve, we get force of friction to be 2.25 newtons. And keep in mind, this just gave us the magnitude of force of friction. We know that it is pointing left, so we can always add a negative sign if we want. Great, thanks for watching.